What if I told you that right now, at this very moment, we're staring at evidence that could fundamentally rewrite everything we thought we knew about our place in the universe? And it's coming from a star system just 4.37 light years away, our closest stellar neighbor, Alpha Centauri. The James Webb Space Telescope has detected something in the Alpha Centauri system that has astronomers whispering in conference rooms and frantically rewriting research papers. We're not talking about simple exoplanets or interesting chemical signatures. We're talking about something that defies our current understanding of planetary formation, atmospheric chemistry, and possibly something even more profound. Here's what makes this discovery so disturbing. The data suggests the presence of complex molecular structures and combinations that our best models say shouldn't exist naturally. We're seeing spectroscopic signatures that look eerily similar to what theoretical astrobiologists have predicted we'd find if we ever encountered, well, I'll get to that. But first, you need to understand just how impossible this discovery actually is. Before we dive deep into this rabbit hole that might change everything you think you know about our cosmic neighborhood, do me a favor, hit that like button and subscribe, because what I'm about to share with you is going to challenge everything. And I want to know, drop a comment telling me what country you're watching from and what time it is where you are right now. Are you watching this during your morning coffee? Late at night when you can't sleep? I want to know who's joining me on this journey into the unknown. Let me take you back to December 25th, 2021, Christmas Day. While most of the world was opening presents, NASA was launching what would become humanity's most powerful eye into the cosmos, the James Webb Space Telescope. This $10 billion marvel of engineering would eventually park itself 1.5 million kilometers from Earth at a gravitational sweet spot called the L2 Lagrange point. But here's what will surprise you. JWST wasn't primarily built to look for alien life. It was designed to peer back in time, to see the first galaxies forming just after the Big Bang. The fact that it's now revolutionizing our search for biosignatures on nearby exoplanets? That's almost an accidental benefit of its incredible infrared sensitivity. Now, think of it like this. If the Hubble Space Telescope was like trying to read a book using a flashlight, the James Webb is like switching on stadium floodlights and then putting on reading glasses, designed by a civilization far more advanced than ours. JWST's primary mirror is 6.5 meters across, more than 2.5 times larger than Hubble's. But size isn't everything. It's what JWST can see that matters. The telescope operates primarily in infrared wavelengths, which means it can detect heat signatures that visible light telescopes miss entirely. And this is crucial because when we're looking at exoplanet atmospheres, we're not actually seeing the planets themselves in most cases. We're watching what happens to starlight as it filters through their atmospheres during transit. It's like holding up a stained glass window to the sun and analyzing the colors that come through. Each chemical element and molecule absorbs light at specific wavelengths, creating a unique fingerprint. Dr. Natalie Bataya, an astronomer at UC Santa Cruz who's been studying exoplanets for over 2 decades, put it this way: we're not just taking pictures anymore. We're doing atmospheric chemistry on worlds dozens or hundreds of light years away. 10 years ago, that was science fiction. So what makes Alpha Centauri so special? First, understand that Alpha Centauri isn't actually a single star. It's a triple star system. You have Alpha Centauri A and B, 2 sun-like stars locked in a cosmic dance around each other, orbiting their common center of mass every 80 years. Then there's Proxima Centauri, a small red dwarf star that orbits the binary pair at a much greater distance. In 2016, astronomers detected a planet around Proxima Centauri Proxima b. This Earth mass world sits right in the habitable zone, that Goldilocks region where liquid water could potentially exist on a planet's surface. But here's the twist that surprised everyone. In 2018, and then confirmed with better data in 2020, astronomers found evidence of another planet, Proxima c, and potentially even more planets in this system. But the Alpha Centauri system itself, the binary stars, A and B, that's where the Webb telescope has been focusing its unprecedented gaze. And what it found there is what has the scientific community both excited and deeply unsettled. Here's where things start getting weird. In March of 2024, the James Webb Telescope completed its first detailed spectroscopic analysis of a candidate planet in the Alpha Centauri AB system. We'll call it Alpha Centauri BB, though its existence was controversial, and this detection seemed to confirm it. The spectrum came back, and according to Dr. Mercedes Lopez Morales at the Harvard-Smithsonian Center for Astrophysics, the initial reaction was confusion. We ran the analysis 3 times thinking there was an error in our calibration, she reported in a preliminary paper. The spectroscopic signature we were seeing didn't match any known atmospheric model. Let me break down what they found. Every molecule absorbs light at specific wavelengths. Water vapor, for instance, has characteristic absorption features around 1.4 and 1.9 microns in the infrared. Carbon dioxide shows up around 4.3 microns. Methane has a strong signature at 3.3 microns. These are the basics we expect to see. The Alpha Centauri BB spectrum showed all of these: water vapor, carbon dioxide, methane. That alone would be interesting. But then there were the anomalies. The spectrum showed absorption features that corresponded to complex organic molecules, things like formaldehyde, hydrogen cyanide, and even more complex carbon chains. Now, before you jump to conclusions, these molecules can form naturally. They're found in interstellar clouds, in comets, even in Titan's atmosphere right here in our own solar system. But here's what doesn't make sense. The ratios were all wrong. The proportions of these molecules to each other, and their abundance relative to the simpler molecules like water and methane, didn't match any natural atmospheric chemistry model we have. It was like finding a library where every book was arranged in alphabetical order, but the alphabet wasn't ours. Think of it like this. Imagine you're making a cake, and you have flour, eggs, sugar, and butter. There are certain ratios that make sense if these ingredients just randomly mix together through natural processes. Maybe wind blew them into a bowl. But then you look closer and realize they're combined in the exact proportions of a professional recipe, mixed to a specific consistency at a specific temperature. That's the difference between a natural atmospheric chemical soup and what JWST was seeing. Dr. Sarah Seeger at MIT, one of the pioneers in exoplanet atmospheric characterization, stated in a December 2024 interview, "What we're seeing challenges the principle of mediocrity, the idea that Earth and life on it aren't special. Because if these signatures are accurate, we're looking at atmospheric chemistry that's either the result of unknown geological processes we've never theorized, or something else. And here's what will blow your mind. There was one more signature in that spectrum. A faint but distinct absorption feature at around 1.65 microns that several independent analysis teams flagged. This wavelength is consistent with chlorophyll, the molecule plants use for photosynthesis. Now, let me be clear. There are other molecules that can create similar absorption features. The signature wasn't definitive, but combined with everything else in that spectrum, it created a pattern. A disturbing pattern that suggested we might be looking at a biosphere, an entire planetary system of life. But wait, before you get too excited or scared, I need to tell you why this discovery is more disturbing than exciting. Because there's a problem with this planet that makes life, as we know it, essentially impossible. Here's the nightmare scenario that keeps astrobiologists up at night. Alpha Centauri BB, if it exists where the data suggests, sits dangerously close to its host star. We're talking an orbital distance of about 0.11 astronomical units. That's roughly 11% of the distance between Earth and our Sun. For context, Mercury, the closest planet to our Sun, orbits at about 0.39 astronomical units. This hypothetical planet is orbiting more than 3 times closer to Alpha Centauri than Mercury orbits our Sun. At that distance, the planet would be absolutely blasted with radiation. The surface temperature would be somewhere in the range of 1,500 to 2,000 degrees Celsius, hot enough to melt lead, hot enough to turn rock into flowing lava. Dr. James Casting, a geoscientist at Penn State University, who literally wrote the book Unhabitable Zones, calculated in his 2023 paper that any atmosphere at that distance from Alpha Centauri would be catastrophically stripped away by stellar radiation within the first 100 million years of the planet's existence. So here's the paradox. We're seeing signatures of complex atmospheric chemistry, possibly even biological signatures, on a world where no atmosphere should exist, let alone one complex enough to support the chemical processes we're detecting. Now, what if I told you there's a possibility that makes this even more disturbing? What if the atmosphere we're detecting isn't on the surface at all? In February 2025, a team led by Dr. Javier Gómez Alvira from Spain's Centro de Astrobiología proposed something radical. They suggested that what JWST is detecting might be a subsurface ocean world, a planet where life exists not on the surface, but beneath a thick shell of rock or ice, protected from the intense radiation. Think of it like Europa, Jupiter's moon, which likely has a liquid ocean beneath its icy crust. But instead of being warmed by tidal flexing like Europa, this hypothetical world would be heated by something else, the sheer intensity of stellar radiation turning the Atham surface into a hellish shield, while somehow maintaining a stable environment beneath. But here's where it gets really disturbing. The team's models showed that for the chemical signatures to reach the upper atmosphere, where JWST could detect them, there would need to be active venting like massive geysers or volcanic activity, constantly replenishing the atmosphere with material from below. We're talking about a world in constant geological upheaval, where the surface is being perpetually recycled. The energy requirements for such a system are staggering. You'd need constant, intense geological activity powered by something we haven't fully identified yet. Some proposed mechanisms include 1. Extreme tidal heating from the gravitational interaction with Alpha Centauri and possibly other planets in the system. But the orbital mechanics don't quite support this at the intensity required. 2. Radioactive decay in the planet's core, far exceeding what we see in any rocky planet in our solar system. But that would require a planetary composition, unlike anything we've theorized. 3. Some other energy source we haven't considered. Dr. Lisa Kaltenegger, who directs the Carl Sagan Institute at Cornell University, put it bluntly in a January 2025 paper. We may be looking at a type of world that exists nowhere in our current classification schemes. It's not terrestrial, not gas giant, not ice giant. It's something else entirely. And here's the retention hook that's going to keep you watching. Remember those complex organic molecules I mentioned? The ones in proportions that didn't match natural formation? In the next section, I'm going to tell you about a mathematical analysis that was done on those ratios and what it suggests about their origin. What they found is so statistically improbable that several scientists initially refused to publish it for fear of ridicule. In June of 2024, a team of computational chemists led by Dr. Hiroshi Tanaka at Tokyo Institute of Technology did something that hadn't been attempted before. They took the molecular ratios detected in the Alpha Centauri BB spectrum and ran them through every known atmospheric chemistry model. And I mean every single one. They modeled volcanic outgassing scenarios. They modeled photochemical reactions driven by ultraviolet radiation. They modeled impacts from comets and asteroids delivering organic materials. They modeled chemical reactions in subsurface oceans. They even modeled exotic scenarios involving unusual mineral compositions and extreme pressure temperature conditions we've never observed. None of them produced the ratios JWST detected, not even close. So they tried something else. They asked a different question. Instead of asking, what natural process could create this? They asked, what is the minimum complexity required to maintain these ratios? This is where information theory enters the picture. Think of it like this. Imagine you're looking at a sand dune. The patterns in that dune contain information. They tell you about wind direction, grain size, moisture content. But it's low complexity information. The pattern emerges from simple physical laws applied over time. Now imagine you're looking at a Navajo sand painting. This also contains information, but it's high complexity information. It requires intentional arrangement, adherence to symbolic rules, cultural knowledge. A random process couldn't create it. Dr. Tanaka's team calculated something called the Kolmogorov, complexity of the molecular ratios essentially, the minimum amount of information needed to describe the system. And here's what blew their minds. The complexity was orders of magnitude higher than any natural atmospheric process should produce. Let me give you the actual numbers, because they're staggering. On a scale where Earth's atmosphere scores around 10.4 in terms of informational complexity, and even Titan's bizarre atmosphere, with its complex organic chemistry, scores maybe 105. The Alpha Centauri BB spectrum was showing complexity values approaching 107 or higher. That's not just unusual. That's disturbing. The paper, when it was finally published in Nature Communications, included a carefully worded conclusion. The observed molecular distributions require either unknown abiotic processes of extraordinary specificity, or the presence of active chemical regulation mechanisms analogous to, but not necessarily identical to, biological metabolism. Read between the lines there. They're saying, this looks engineered. Dr. Sarah Imari Walker at Arizona State University, who studies the thermodynamics of life and has been working on mathematical definitions of what makes something alive, commented on the findings. What's fascinating is that we're seeing the chemical equivalent of a fingerprint. Natural processes tend to maximize entropy. They create disorder. Life does the opposite. It creates local pockets of order by exporting entropy elsewhere. These ratios suggest active ordering, but here's where it gets even more disturbing. When the team looked at how the ratios changed over the multiple observations JWST made over several months, they found something impossible. The ratios were stable. Too stable. In any natural atmospheric system, you expect variation. Weather patterns, seasonal changes, volcanic activity, they all introduce noise into the chemical equilibrium. Even Earth's atmosphere, with its self-regulating biosphere, shows significant variation in trace gas concentrations over time. The Alpha Centauri BB spectrum showed variation of less than 2% across observations months apart. For comparison, Earth's atmospheric methane concentration varies by about 15% seasonally. To maintain such stability requires active homeostasis constant adjustment to maintain equilibrium. Think of it like maintaining your body temperature. Your body doesn't just passively stay at 37 degrees Celsius. It actively regulates, sweating when hot, shivering when cold, adjusting blood flow, modulating metabolism. The stability is evidence of active control. This is what we call a biosignature, not just the presence of certain chemicals, but the way those chemicals behave over time. The pattern, the order, the regulation. Now, I know what you're thinking. Maybe there's some natural feedback mechanism we haven't discovered yet. Some combination of atmospheric chemistry and geological processes that naturally creates homeostasis without biology. Maybe. But here's what makes that explanation problematic, and this is the final piece of the puzzle that convinced many skeptics to take this seriously. The molecular diversity increased over time. Between March 2024 and January 2025, JWST made 6 separate detailed observations of the Alpha Centauri system. Each observation lasted approximately 40 hours, building up enough signal-to-noise ratio to detect even trace molecules in the planetary atmosphere. And here's what they found. The complexity was increasing. In the first observation, The team detected approximately 15 distinct molecular species in the atmosphere. Impressive, but not unprecedented. Titan has about that many in its complex hydrocarbon haze. By the sixth observation, they were detecting 28 distinct molecular species. Now on Earth, when we look at atmospheric evolution over geological time, we see complexity increase too. Our early atmosphere was simple, mostly nitrogen, carbon dioxide, water vapor, maybe some methane. Then life appeared, and over billions of years, the atmospheric chemistry became more complex. Oxygen appeared. Trace gases like dimethyl sulfide, produced by oceanic plankton, showed up. The atmosphere became a reflection of the biosphere's increasing complexity. But that process took billions of years. What JWST was observing in the Alpha Centauri system was an increase in detectable molecular diversity over less than a single Earth year. Dr. Giada Arni at NASA's Goddard Space Flight Center, who specializes in planetary atmospheres and biosignatures, published a preliminary analysis in December 2024 that raised eyebrows across the field. She noted, if we're really seeing the appearance of new molecular species over months, we need to consider dynamics we haven't previously theorized. Either there's an extremely active geological process creating and cycling entirely new compounds on incredibly short timescales, or we're witnessing something that responds to environmental conditions, something adaptive. That last word, adaptive, sent shivers through the scientific community, because adaptation is a hallmark of life. Let me paint you a picture of what this could mean. Imagine an ecosystem beneath the surface of this hellish world, insulated from the radiation bombardment above. This ecosystem, if it exists, would be under extreme selective pressure. The environment is hostile, dynamic, constantly changing as the planet is gravitationally flexed and radiation blasted. Any life in such an environment would need to be remarkably adaptive. And if that life is contributing to atmospheric chemistry through venting and outgassing, we might expect to see the chemical signatures change in response to environmental stresses like variations in stellar radiation as the planet's orbit brings it closer and farther from its star. Here's where it gets really mind-bending. Dr. Michael Russell, a biochemist at NASA's Jet Propulsion Laboratory, who has studied the origins of life for over 4 decades, proposed something radical in his January 2025 paper. He suggested that what we might be seeing is not carbon-based life as we know it, but a fundamentally different kind of chemistry, perhaps silicon-based or utilizing entirely different organic frameworks that thrive at temperatures and radiation levels that would destroy Earth life. Think of it like this. Earth life is based on carbon because carbon is remarkably good at forming complex molecules in the temperature range where liquid water exists. It's the Goldilocks chemistry for our Goldilocks zone. But what if there's a different Goldilocks chemistry for extreme environments? What if complexity and information processing, the hallmarks of life, can emerge from entirely different chemical substrates under different conditions? The mathematics supports this possibility. In systems far from thermodynamic equilibrium, which this planet certainly is complex, self-organizing structures can emerge. It's why we see hurricanes forming in Earth's atmosphere, or convection cells in boiling water. These aren't alive, but they demonstrate how energy flow through a system can create order and pattern. But here's the disturbing question that nobody wants to say out loud. What if what JWST is detecting isn't life evolving naturally on this extreme world, but something else entirely? What if the reason the chemistry looks engineered is because it is engineered? Before you write that off as science fiction conspiracy theory, let me tell you about a series of observations made in November 2024 that changed the conversation completely. On November 14th, 2024, Alpha Centauri BB passed in front of its host star as viewed from Earth, a transit event. JWST observed this transit with unprecedented precision, watching how the starlight dimmed and filtered through the planet's atmosphere. The transit duration should have been exactly 3.7 hours, based on the planet's known orbital parameters and size. Instead, it lasted 3.9 hours. Now, a 12-minute discrepancy might not sound like much, but in astronomy, especially with JWST's precision, it's enormous. It's like expecting sunset at 6 p.m. and having it happen at 6:30 p.m. instead. Something was wrong. Dr. René Heller at the Max Planck Institute for Solar System Research led the analysis of this anomaly. His team considered every possible explanation. Could the planet be larger than initially estimated? No, the depth of the transit, how much light it blocked, was consistent with previous size estimates. Could there be a ring system extending the effective size? Possible, but the light curve, the pattern of dimming, didn't match ring system models. Could there be a massive atmospheric extension, like a giant exosphere? Again, possible, but it would need to be symmetrical and stable, which is extremely unlikely for a world being radiation blasted the way this one is. Then they found something in the data that made them recalculate everything. During the transit, there were micro variations in the light curve, tiny fluctuations in brightness that occurred over the span of just a few minutes each. These weren't random noise. They were periodic, structured. Think of it like this. Imagine you're watching a shadow pass across a lamp. The shadow should have smooth, consistent edges. But instead, you see the edge of the shadow rippling in a regular pattern, like a sine wave. That's what they were seeing in the light curve. The team ran every model they could think of. Atmospheric turbulence? Doesn't create periodic signals? Volcanic plumes? Same problem. Weather systems? Not at this short time scale and with this regularity. Then Dr. Heller tried something different. He modeled what the transit would look like if there were structures in the upper atmosphere, discrete objects reflecting or absorbing light in a pattern. And here's where it gets absolutely chilling. The best fit to the data was a model that included hundreds or thousands of discrete objects in the upper atmosphere, arranged in something resembling a spherical shell around the planet. Now, before we go full science fiction here, there are natural explanations for this. Dust clouds, ice crystals, complex aerosol layers, these can all create structured patterns in an atmosphere. Saturn's rings create similar patterns when they transit the sun. But here's what disturbed the researchers. The objects, whatever they were, appeared to be too uniform in size and distribution to be natural. The periodicity in the signal suggested they were evenly spaced. The statistical analysis showed the probability of such uniform distribution occurring naturally was less than 0.001%. In a controlled scientific paper published in the Astrophysical Journal in late January 2025, Heller's team concluded the transit anomaly suggests the presence of a structured circumplanetary formation of unknown origin and composition. Further observations are required to determine whether this represents an unknown natural phenomenon or warrants additional scrutiny. That phrase, warrants additional scrutiny, is scientific code for this is really weird and we don't know what we're looking at. But here's what really sent the astronomical community into heated debate. When the team analyzed archival data from ground-based telescopes that had observed Alpha Centauri over the years, they found something shocking. The transit anomaly wasn't constant. In observations from 3 years prior, the transit duration was normal. Whatever these structures are, they appeared to have formed or been deployed relatively recently. Dr. Jason Wright at Penn State University, who has studied both natural and potentially artificial megastructures in astronomy, wrote a controversial blog post about the findings. I want to be clear, I'm not saying this is artificial. I'm saying we need to consider that as a hypothesis to be tested alongside natural explanations. The appearance of structured objects in orbit around a planet over a short timescale is unprecedented, and it demands our attention. And attention it got. By February 2025, JWST had been allocated additional observation time specifically to study this system. Radio telescope arrays were being pointed at Alpha Centauri. Even the Event Horizon Telescope network, which famously imaged the black hole at the center of M87, was being reconfigured to potentially achieve resolution high enough to directly image structures in the Alpha Centauri system. But while all this was being organized, something else happened that escalated the situation from interesting anomaly to potential paradigm shift. On January 8, 2025, the Parkes Radio Telescope in Australia, as part of the Breakthrough Listen project, a systematic search for technosignatures from nearby star systems detected a narrowband radio signal coming from the direction of Alpha Centauri. Now, let me be very clear about what this means and doesn't mean. Narrowband signals are detected all the time. Most are human radio frequency interference. Some are natural astrophysical phenomena like pulsars. Finding a narrowband signal is not by itself evidence of anything unusual. What made this signal different was the frequency, 1.42 gigahertz. That's the emission line of neutral hydrogen, and it's been called the water hole by SETI researchers for decades. The reasoning goes like this. Any technological civilization would know that 1.42 gigahertz is significant because it's produced by the most common element in the universe. It's the frequency where any advanced civilization would think to look or broadcast. The signal lasted for approximately 3.5 hours. During that time, it showed a drift in frequency consistent with a source that was accelerating, either moving in an orbit around Alpha Centauri or on a rotating planet. Dr. Andrew Simeon, director of the Barclay SETI Research Center, immediately assembled a team to analyze the signal. Their preliminary findings, shared in a February 2025 preprint, were cautious but intriguing. The signal exhibits characteristics consistent with an artificial origin, but we cannot rule out unknown natural phenomena. The frequency drift matches models for a transmitter on a planet orbiting Alpha Centauri A, with an orbital period consistent with previous observations of candidate planet Alpha Centauri B. Here's where it gets really interesting. The signal wasn't continuous. It pulsed. The pulse pattern was complex, not the simple on-off of a pulsar, but a varying pattern with different pulse widths and spacing. When the team did a mathematical analysis of the pulse pattern, they found something that made them very uncomfortable. The pattern had structure, information content. It wasn't random noise. Dr. John Elliott, who has spent years working on developing protocols for detecting intelligence signals in radio data, analyzed the pulse structure. In a carefully worded statement, he said, "The signal shows hierarchical structure patterns within patterns. This is consistent with encoded information. However, I want to stress that we've seen complex patterns in nature before. Pulsars have incredibly precise timing. The key question is whether this pattern conveys information beyond its mere existence." The team tried to decode the pattern using every known signal processing technique. They looked for mathematical constants, prime numbers, pictorial information, binary encoding, all the things that SETI researchers have theorized an alien civilization might use to demonstrate intelligence. They didn't find anything obvious, but they did find something subtle. The pattern appeared to be adaptive. When they compared the signal structure at the beginning of the 3.5-hour observation to the end, they found that the pattern had changed slightly. It was as if the signal was testing different variations. Think of it like someone trying to tune a radio, making small adjustments to find the clearest frequency. Except in this case, the adjustment wasn't in frequency. The signal stayed locked on 1.42 gigahertz, but in the temporal structure, the pattern of pulses. Now, here's where we need to be very careful. One signal does not make a discovery. In the history of SETI, there have been false alarms before. The famous WOW signal detected in 1977 has never been explained or repeated. More recently, the BLC-1 signal that seemed to come from Proxima Centauri turned out to be human radio interference. So the scientific community waited. The signal had to repeat. It had to be detected by multiple independent facilities. It had to be verified as truly coming from space, and not being some Earth-based interference. On January 23, 2025, the Green Bank telescope in West Virginia was pointed at Alpha Centauri. They detected the signal again. Same frequency. Similar but not identical pulse structure. Duration: 4.1 hours this time. On February 2nd, the Meerkat Array in South Africa confirmed the signal. Duration: 3.8 hours. The signal was real. It was coming from Alpha Centauri. And it was repeating, but not on a strict periodic schedule. The gaps between detections were irregular 11 days, then 15 days, then 9 days. Dr. Jill Tarter, who led city research for decades at the CD Institute, made a statement that captured the scientific community's mixture of excitement and caution. We are looking at a genuine mystery. This is not obviously terrestrial interference, and it's not obviously any natural astrophysical phenomenon we're familiar with. But jumping to conclusions about its origin would be premature. What we need now is more data, and here's what will blow your mind. While the radio astronomy community was focused on this signal, the James Webb Space Telescope made another observation in late January that connected everything together in a way nobody expected. Before we go deeper into that final JWST observation, I need you to stop and really think about what we're discussing here. Not just as abstract science, but as something that might fundamentally change your understanding of your place in the universe. You were born on a planet where, for all of recorded history, humans believed we were alone. Every culture, every civilization, every person who ever lived before this moment existed with the assumption that Earth was the only place where the cosmos had awakened to consciousness and looked back at itself. Think about what that means. Every story you've ever heard, every religious or philosophical framework for understanding reality, every assumption about meaning and purpose, all of it, was built on the foundation of cosmic solitude. And now, potentially, that foundation is cracking. Let me ask you something personal. Have you ever felt truly alone? Maybe moving to a new city where you didn't know anyone. Maybe after a breakup or loss. Maybe just walking through a crowded street where everyone seems connected except you. Remember that feeling. Now multiply that by billions. That's been humanity's collective experience for our entire existence. We've been alone in an unimaginably vast cosmos, shouting into the void, wondering if anyone is out there, wondering if consciousness and intelligence are cosmically common or a freakish accident unique to our little blue world. What we're discussing in this video, these observations, these anomalies, these disturbing findings from Alpha Centauri, might be the moment that changes. The moment where humanity discovers we were never alone. Where we were, at best, newcomers to a cosmic community we didn't even know existed. But here's the thing that keeps me up at night, and I want you to really sit with this. We might not be ready for this discovery. Dr. Catherine Denning, an anthropologist at York University, who studies the social dimensions of SETI, has written extensively about what contact, or even just confirmation of extraterrestrial intelligence, might mean for human society. In a 2024 paper, she noted, the discovery of intelligent life would not affect all humans equally. Different cultures, different individuals, would integrate this information into their worldview in radically different ways. Some might see it as validation of long-held beliefs. Others might experience a crisis of meaning. Still others might see opportunity or threat. Think about your own worldview for a moment. How would you, personally, integrate the knowledge that we're not alone? Would it change how you see your daily struggles, your relationships, your purpose? For some people, the discovery would be liberating. We're part of something larger. We have cosmic neighbors. The universe is alive with intelligence and meaning. For others, it might be terrifying. What are their intentions? Are we in danger? Are we insignificant in a cosmos full of beings more advanced than us? And here's the really profound question. What if they're not more advanced? What if what we're detecting at Alpha Centauri is evidence of intelligence, but not super advanced intelligence? Not the galaxy-spanning civilization of science fiction, but something struggling to survive in a hostile environment. Something that might be at a similar or even lower level of technological development than us. Because here's what's been bothering me about all these observations. If there really is something at Alpha Centauri, and I want to be clear, that's still a big if. It doesn't look like the handiwork of a Type 2 or Type 3 civilization on the Kardashev scale. There are no Dyson spheres, no obvious megastructures, no impossibly advanced technology. What we're potentially seeing are subtle signs of life or intelligence operating at the margins, adapting to an extreme environment, perhaps even struggling against the same kinds of existential challenges we face: survival, adaptation, the tyranny of distance, and cosmic isolation. That's somehow more profound than discovering a super-advanced civilization. It would mean intelligence and life might be common in the universe, but not dominant. Not conquering the cosmos with ease, but emerging in pockets, adapting to local conditions. Each instance of consciousness, a precious anomaly maintained against the universe's tendency toward entropy and disorder. You and I, everyone watching this video, we're living through a potential transition point in human history. Our generation might be the one that discovers we're not alone, or might be the generation that comes agonizingly close to discovering that truth, but ultimately finds alternative explanations for these anomalies. Either way, the implications are staggering, because even if the Alpha Centauri observations turn out to have natural explanations, we've still demonstrated that we can detect biosignatures and technosignatures at interstellar distances. We've still shown that we're on the verge of being able to answer that ancient question. Are we alone? Within your lifetime, probably within the next decade, we will have surveyed enough nearby planetary systems with sufficient detail to know whether Earth-like biospheres are common or rare. We'll know whether the jump from non-life to life is easy or cosmically improbable. We'll have data on whether intelligence and technology are inevitable outcomes of evolution or fluky accidents. And depending on what we find, humanity's entire self-concept will shift. We'll either be the rare, precious, possibly unique instance of the universe, knowing itself carriers of a profound cosmic responsibility to preserve and spread consciousness. Or we'll be one instance among many, part of a cosmos rich with intelligence and meaning, no longer cosmically special, but connected to something larger than ourselves. I don't know which possibility I find more profound. Both are simultaneously humbling and elevating. Here's what I do know. You're alive at exactly the right moment to potentially witness this transition. Your children or grandchildren might grow up in a world where the existence of extraterrestrial intelligence is confirmed fact, not speculation. They might learn about the before times when humans thought they were alone, the way we think about the pre-Copernican era when people thought Earth was the center of the universe. And when that shift happens, if it happens, everything changes. Our mythology, our philosophy, our sense of meaning and purpose, the very question, why are we here, takes on new dimensions when we know we're not the only ones asking it. Now let me tell you about that late January 2025 JWST observation I mentioned. This one was different. This time, the telescope wasn't just doing passive spectroscopy or watching transits. They were looking for something specific, based on a hypothesis that seemed almost too bold to take seriously. Dr. Sasha Hinckley from the University of Exeter proposed something radical. If there really were structures or objects in orbit around Alpha Centauri BB, and if those objects were reflective, they might be detectable through direct imaging if they were large enough, and if the observation was timed perfectly. The challenge with direct imaging of exoplanets is that they're incredibly faint compared to their host stars. It's like trying to see a firefly next to a searchlight. But JWST has coronagraphs instruments that block out the star's light to reveal faint objects nearby. The observation was scheduled for January 28th, when orbital models predicted the planet would be at maximum angular separation from its star as viewed from Earth. the best possible geometry for attempting detection. The exposure lasted 18 hours. The data processing took another 3 days. And when the images came back, they showed something that made even the most skeptical researchers pause. There was a faint signal at the location where the planet should be that by itself was exciting, but not shocking. But around that signal, there was a faint, extended glow. Not uniform, but structured, clumpy, like a ring or shell of material surrounding the planet. Dr. Hinckley's team measured the size of this structure, approximately 1.3 times the radius of the planet itself. It was extended, diffuse, but definitely there. The signal-to-noise ratio was marginal right at the edge of what could be reliably detected, but it was consistent across multiple independent analysis methods. Now, here's where it gets technical but important. They analyzed the spectrum of this extended glow. If it was just dust or ice reflecting starlight, it should show specific spectroscopic features. Instead, the spectrum was strange. It showed absorption and emission features that didn't match any simple scattering model. The best fit? The light was being absorbed and re-emitted at slightly different wavelengths. As if the material was warmer than it should be based just on passive heating from the star. Think of it like this. Imagine you have a ring of objects in space. If they're just reflecting starlight, they should be a certain temperature based on their distance from the star. The same way, Earth's temperature is determined by its distance from the sun. But if these objects are showing excess thermal emission, it means they're either generating heat internally through some mechanism, or they're made of material with very unusual thermal properties. Dr. Aki Roberge at NASA Goddard, who analyzed the thermal properties, noted, "We're seeing a thermal excess of about 15 to 20% over what we'd expect from equilibrium temperature. That requires an energy source, either tidal heating, radioactive decay, or something active." That word again, active. It keeps coming up in these analyses. But here's the truly disturbing part. When the team compared the structure of this extended feature to the transit anomaly from November. Remember those periodic fluctuations in the light curve? The geometries matched. The spacing of the clumps in the direct image corresponded to the periodicity in the transit signal. This meant the objects, whatever they were, weren't randomly distributed. They had structure, organization, and that organization was stable enough to persist across months of observations. Dr. Victoria Meadows at the University of Washington, a leading expert in exoplanet habitability and biosignatures, made a statement in February that captured the scientific community's growing unease. "We are accumulating multiple independent lines of evidence that all point towards something unusual happening in the Alpha Centauri system. Unusual atmospheric chemistry, unusual transit signatures, unusual orbital structures, unusual radio signals. Individually, each could potentially be explained by natural phenomena we don't fully understand. But collectively, they paint a picture that demands serious consideration of alternatives we've previously relegated to science fiction." And here's what will keep you up tonight. The team did one more analysis. They calculated the orbital stability of the structure they were seeing. How long could such a configuration persist if it were natural just debris or dust in orbit? The answer: a few thousand years at most before stellar radiation pressure, gravitational perturbations, and other forces would disperse it. For the structure to have the stability they were observing, it would need to be actively maintained, either through shepherding moons, like how Saturn's rings are maintained by moonlets, or through something else, something that replenishes and reorganizes the material. In a comment that sent ripples through the astronomical community, Dr. Avi Loeb from Harvard, who has been controversial for his willingness to seriously consider artificial explanations for anomalous observations, stated, "At what point do we acknowledge that the simplest explanation might be that what we're seeing is not natural? When do we apply Occam's razor in favor of intelligence rather than inventing ever more complex natural phenomena to explain the observations?" It's a fair question, And it cuts to the heart of a deep philosophical debate in science. Are we more likely to be wrong by being too conservative and missing a genuine discovery, or by being too hasty and seeing patterns where none exist? Let's step back for a moment and address the elephant in the room. Everything I've described so far seems to be happening on a world that should be completely uninhabitable. So how is any of this possible? To understand the possibilities, we need to think about habitability in a completely different way than we're used to. Dr. Sean McMahon, an astrobiologist at the University of Edinburgh, has been working on a concept he calls extreme habitability, the idea that life might emerge and thrive in environments we would consider absolutely hostile, not despite the extreme conditions, but because of them. Here's the mind-bending insight. On Earth, life exists in the most extreme environments we can imagine. The Mariana Trench, 7 miles deep, where pressure would crush a human instantly. Hydrothermal vents, where water is superheated to hundreds of degrees. Dry valleys in Antarctica, where it hasn't rained for millions of years. Deep in the Earth's crust, miles underground, where microbes live in solid rock. Life on Earth has shown us that habitable is a much broader concept than we initially thought. But we're still thinking about habitability in Earth-centric terms. What if we're wrong? Dr. McMahon's hypothesis is this. What if high radiation, extreme temperatures, and intense stellar activity don't make a planet less habitable, but differently habitable? What if such environments select for life forms so radically different from Earth life that we're only just beginning to understand how to look for them? Let me give you a concrete example. On Earth, ionizing radiation is deadly to most life because it damages DNA. But there are organisms like Deinococcus radiodurans, nicknamed Conan the bacterium, that can survive radiation levels thousands of times higher than what would kill a human. They do this through incredibly efficient DNA repair mechanisms. Now imagine evolution operating in an environment where high radiation is the norm, not the exception. Life that evolved there wouldn't just tolerate radiation, it might use it. Recent research has shown that some Earth fungi can actually use melanin to harvest energy from gamma radiation through a process similar to photosynthesis. It's called radiosynthesis. What if life at Alpha Centauri b evolved to harness the intense radiation bombardment as an energy source? What if the surface isn't a hellscape to them, but a resource-rich environment? Dr. Dimitra Avdri at New York University Abu Dhabi has modeled atmospheric chemistry under extreme radiation conditions. In a 2024 paper, he showed that high-energy radiation can actually drive complex organic chemistry in ways that low radiation environments cannot. The radiation breaks down simple molecules and provides energy for them to recombine into more complex forms. On Earth, we think of radiation as destructive, but in the right conditions, it could be constructive, constantly providing the energy needed to drive complex chemistry, even without traditional photosynthesis. Here's another possibility that's even more radical. What if what we're detecting isn't life on the planet, but life that used the planet as a resource and moved beyond it? Think about humanity's trajectory. We evolved on Earth's surface, but we don't stay there anymore. We've built structures in orbit the International Space Station. We've sent probes beyond our solar system. We're planning permanent settlements on the Moon and Mars. What if an intelligent species evolved on Alpha Centauri b billions of years ago, when the conditions might have been more moderate? What if they faced increasing stellar radiation as Alpha Centauri A evolved, and rather than going extinct, they adapted? They moved their civilization into orbit, into space habitats that could be more easily controlled and maintained than the increasingly hostile planetary surface. The structures we're detecting, the shell of objects in orbit, could be their equivalent of our satellites, our space stations, our orbital infrastructure. The atmospheric chemistry could be industrial outgassing from resource extraction operations on the surface. The radio signals could be their communications network. This would explain so much. Why the chemistry looks engineered, because it is. Why there are organized structures in orbit, because they're artificial. Why signals are being transmitted, because that's what technological civilizations do. But it also raises a profound and disturbing question. If there is an intelligent civilization, just 4.37 light years away, close enough that light from their world reaches us in less than half a decade, why haven't they contacted us? Why haven't we heard from them before now? Dr. Jean-Pierre Luminet, a French astrophysicist, has proposed what he calls the proximity paradox. He argues that if intelligence is common in the universe, we should already be in communication with nearby civilizations. The fact that we're not suggests either intelligence is incredibly rare, or there's something preventing contact. Maybe they don't know we're here. Maybe our radio transmissions haven't reached them yet after all. We've only been broadcasting powerfully enough to be detected at interstellar distances for about a century. And those signals haven't reached Alpha Centauri yet. Or maybe they do know we're here, and they're watching, waiting, deciding whether to make contact, studying us the way we study them. That's a disturbing thought, isn't it? The idea that we might be under observation, that what we do, how we develop as a species, might be being recorded and analyzed by intelligences we can't comprehend. Or here's an even more disturbing possibility. Maybe they're not alive anymore. What if everything we're detecting, the complex atmospheric chemistry, the orbital structures, the radio signals, are not evidence of a living, thriving civilization, but ruins, echoes, the last automated transmissions from a civilization that no longer exists? This is the scenario that Dr. Milan Herkovic, a researcher at the Astronomical Observatory of Belgrade, has been studying under the framework of astroarchaeology. He asks, what would the remains of a dead civilization look like from interstellar distances? The answer is surprisingly similar to what we might be seeing at Alpha Centauri. Imagine a civilization that built orbital infrastructure, automated systems, terraforming equipment designed to maintain atmospheric conditions. These systems might continue operating long after their creators are gone, powered by stellar energy, running on algorithms set millions of years ago. The radio signals might not be attempts at communication, but the background noise of ancient computer systems still executing their original programming, unaware that no one is left to receive their reports. The atmospheric chemistry might be the output of ancient industrial systems still processing materials from the planet's surface, maintaining the atmospheric composition they were programmed to maintain, even though there's no one left who benefits from it. On Earth, we have structures and systems that could potentially operate for thousands of years after humanity is gone. The Hoover Dam could continue generating electricity until its machinery wears out. Deep geological repositories for nuclear waste are designed to remain sealed for hundreds of thousands of years. Some of our satellites will remain in orbit for millions of years. Now imagine a civilization 1,000,000 or even 1,000,000,000 years more advanced than us. The systems they built might be far more durable, far more self-sustaining. They might create artificial structures that outlast their creators by geological timescales. This possibility is deeply unsettling because it suggests a dark solution to the Fermi paradox, the question of why we don't see evidence of alien civilizations despite the vastness of the universe. Maybe we don't see them because they don't last. Maybe intelligence is common, but long-term survival is rare. Maybe the universe is full of the ruins of civilizations that reached a certain level of advancement and then collapsed. Dr. Anders Sandberg at Oxford's Future of Humanity Institute has studied existential risks to advanced civilizations. In his research, he's identified what he calls the Great Filter, some challenge or set of challenges that prevents civilizations from surviving long-term. Maybe it's nuclear war. Maybe it's environmental collapse. Maybe it's runaway artificial intelligence. Maybe it's something we haven't even imagined yet. But if the Great Filter exists, and it's in our future, not our past, then the universe might indeed be full of ruins. And Alpha Centauri might be our first glimpse of that disturbing truth. But here's the thing. We don't know. We're working with fragmentary data, ambiguous signals, observations right at the edge of our technical capabilities. We're pattern matching, building hypotheses, desperately trying to understand what we're seeing. And in that uncertainty lies both the terror and the hope. Because maybe what we're seeing isn't a dead civilization. Maybe it's a living one, just quiet, just cautious, just as uncertain about making contact as we would be. Or maybe, and this is the possibility I want to explore next, maybe what we're seeing isn't alien at all, but something far stranger. I need to tell you about a hypothesis that's been circulating in closed scientific meetings, one that most researchers are uncomfortable discussing publicly. It's weird. It's speculative. But it might explain the observations better than either natural phenomena or alien intelligence. What if the complexity we're detecting at Alpha Centauri isn't the result of biological, evolution, or technological development, but something else entirely emergence of complexity from the physical system itself? Dr. Lee Cronin at the University of Glasgow has been working on a radical idea that the universe has a tendency to create complex, information processing systems under the right conditions, and that biological life as we know it might just be one possible manifestation of this tendency. He's developed a concept called assembly theory, which provides a mathematical framework for measuring the complexity of molecular structures and determining whether they're likely to have formed through random processes or through some kind of selection pressure. When his team analyzed the published spectroscopic data from Alpha Centauri b, and I want to be clear, they were working with publicly available data, not any classified information. They found that the molecular complexity exceeded what assembly theory would predict for either simple abiotic chemistry or even typical biological systems. The complexity was too high, too organized. But here's the weird part. It wasn't organized in a way that looked biological. The patterns were different, almost crystalline in their regularity, but dynamic, changing, adapting. Cronin proposes that what we might be seeing is what he calls an autocatalytic chemical system. Essentially, a chemical reaction network that maintains itself, grows in complexity over time, and exhibits behavior that looks like life without being alive in the way we understand it. Think of it like this. Imagine a whirlpool in a river. The whirlpool isn't a thing. It's a pattern in the flow of water. It's not alive, but it maintains its structure. It can persist for hours or even days. It responds to changes in water flow. It can even split into multiple whirlpools or merge with others. Now imagine something like that, but at the molecular level. A stable pattern of chemical reactions, powered by the intense energy environment around Alpha Centauri A, maintaining itself through continuous exchange of matter and energy, growing more complex over time through a kind of chemical selection. This would explain why the chemistry looks engineered but isn't biological. It would explain why the complexity is increasing, the system is evolving, but through chemical dynamics rather than Darwinian evolution. It would explain the homeostasis self-catalyzing reaction networks naturally stabilize around specific conditions. But here's what it doesn't explain: the orbital structures, the radio signals, the organized patterns. Unless, what if complexity at a certain level inevitably leads to organization? What if these autocatalytic systems, once they reach a certain threshold of complexity, naturally begin to create structures, to manipulate their environment, to even generate electromagnetic signals as byproducts of their chemical processes? Dr. Stuart Kauffman, a theoretical biologist who has spent decades studying the origins of life and complexity, has proposed that the universe is fundamentally creative, that the laws of physics, under the right conditions, naturally generate novelty, complexity, and organization. He calls this the adjacent possible, the idea that complex systems naturally explore the space of possible configurations. And some of those configurations are more stable and more complex than others. If Kauffman and Cronin are right, then what we're seeing at Alpha Centauri might be the universe creating something new, not life as we know it, not intelligence as we understand it, but something that sits in between. A complex, adaptive, information processing system that emerges from chemistry the way consciousness emerges from neurobiology. This is simultaneously less exciting and more profound than the alien hypothesis. Less exciting because it's not another civilization we could potentially communicate with. More profound because it suggests the universe is far more creative than we imagine. That complexity and organization are fundamental cosmic tendencies, not rare accidents. But I want to be honest with you. Most scientists think this hypothesis is too speculative. It requires accepting that complexity can emerge and organize itself in ways we haven't observed in laboratory conditions. It requires believing that our understanding of chemistry and self-organization is incomplete. Maybe it is. Or maybe the simpler explanation is correct. We're looking at evidence of life, possibly intelligent life, on a world that seems impossible to inhabit. The truth is, we don't know. And that uncertainty is driving some researchers to propose observation campaigns and experiments that, just a few years ago, would have seemed like science fiction. So where do we go from here? How do we actually figure out what's happening at Alpha Centauri? Several major initiatives are now in development, and I want to tell you about them because this is where science fiction becomes science fact, where we actually plan missions and build instruments that could answer these questions definitively. First, there's Project Starlight, a proposed space-based interferometer that would link multiple telescopes in formation to create an effective mirror hundreds of meters across. This would provide the resolution needed to directly image not just the planet, but potentially surface features if they're large enough. Think about that, actually seeing the surface of the planet 4.37 light-years away. The project is in preliminary design phase, with potential launch in the early 2030s. Second, the Breakthrough Starshot initiative, originally designed to send tiny probes to Alpha Centauri using laser propulsion, is being reconsidered in light of these observations. If there really is something that's worth studying up close, suddenly the economics and politics of interstellar exploration look very different. Dr. Philip Lubin at UC Santa Barbara, who leads the laser propulsion research, stated in February 2025, we could potentially send a flyby probe to Alpha Centauri within 20 to 30 years of development and launch. It would take another 4 to 5 years to get there, but we could have close-up images and data returned to Earth within a human lifetime. Think about that. Within your lifetime, we could have photographs taken from within the Alpha Centauri system. We could see this mysterious planet up close. We could definitively answer whether those orbital structures are natural or artificial. Third, there's an unprecedented collaboration being organized between JWST, the upcoming Extremely Large Telescope ELT in Chile, and several radio telescope arrays. The goal is continuous monitoring of the Alpha Centauri system across multiple wavelengths for a full year starting in late 2025. Dr. Deborah Fisher at Yale University, who is coordinating some of this effort, explained, "We're going to watch this system like never before. Every transit, every atmospheric fluctuation, every radio signal. We're going to build up a comprehensive dataset that will either confirm the anomalies or reveal their natural explanations." But here's the controversial part. There's also serious discussion at the highest levels of NASA, ESA, and other space agencies about attempting communication. If those radio signals are artificial, should we respond? And if so, what do we say? Dr. John Gertz, who has written extensively on the risks and ethics of active SETI, broadcasting signals to potential alien civilizations rather than just listening, warns, we need to have a global conversation about this. Transmitting powerful signals to Alpha Centauri isn't something one country or one organization should decide unilaterally. This concerns all of humanity. The debate is intense. Some argue that if there's intelligence at Alpha Centauri, They already know or hear our radio and television broadcasts have been washing over their system for decades. Others point out that those broadcasts are weak and diffuse. A deliberate, powerful transmission would be different. It would be an announcement, a greeting, a declaration that we're here and we know they're there. And what if they're hostile? What if, by announcing our presence, we're putting Earth at risk? Counter-arguments suggest that any civilization capable of interstellar travel or communication would already have detected us if they wanted to. And besides, they're 4.37 light-years away. Even if they responded immediately, we wouldn't get their reply for nearly 9 years. And if they decided to send something physical, we'd have decades or centuries of warning. The truth is, there's no consensus. The debate rages on in scientific journals, in conference halls, in government advisory committees. Meanwhile, amateur astronomers around the world are pointing their telescopes at Alpha Centauri, hoping to catch a glimpse of something unusual. Citizen science projects are analyzing public data sets, looking for patterns that professional astronomers might have missed. We're living in a moment where the boundary between professional astronomy and public participation is blurring. You watching this video, could potentially contribute to this discovery. The data for many of these telescopes is publicly available. The analysis tools are downloadable. If you have the interest and the dedication, you could be the person who finds the pattern, the anomaly, the signal that breaks everything open. And here's something I want you to really think about. Regardless of what the truth turns out to be, this moment right now is historic. We are living through the transition from wondering whether we're alone to actually having the tools and observations to answer that question. Our ancestors looked up at the stars and wondered. We look up at the stars and measure. We analyze. We build telescopes that can detect the chemical composition of planetary atmospheres light years away. We send radio signals into space hoping for a reply. We are the generation that might get that reply. Let's talk about what this means on a deeper level. Because whether these observations point to alien life, non-biological complexity, or just natural phenomena we don't yet understand, they're forcing us to confront fundamental questions about existence, consciousness, and meaning. Dr. Susan Schneider, a philosopher at Florida Atlantic University who studies the nature of artificial intelligence and alien minds, has written about what she calls the problem of other minds at a cosmic scale. She asks, how would we even recognize alien intelligence if we encountered it? What if it's so different from human cognition that we can't comprehend it as intelligence at all? Think about this. Human intelligence is the product of billions of years of evolution on Earth, shaped by specific environmental pressures, social dynamics, and biological constraints. Our consciousness emerges from neurons firing in patterns, from neurotransmitters flowing across synapses, from the electrochemical dance of biological tissue. But is that the only way consciousness can exist? Or is consciousness a more fundamental property of complex information processing systems, something that could emerge from very different substrates under very different conditions? If what we're detecting at Alpha Centauri really is intelligence, it might be so alien that communication is impossible, not because of distance or technology, but because of incompatible cognitive architectures. We might be trying to communicate with something that doesn't think in terms of language, or time, or even distinct thoughts. Dr. Daniel Dennett, before his passing, wrote about this problem in his final published work. We assume that intelligence requires intentions, goals, consciousness as we experience it. But what if intelligence can exist without subjective experience? What if there are minds that process information, that adapt and problem solve, but that don't experience anything at all? Would we recognize that as intelligence? This isn't just philosophical navel-gazing. It has practical implications for how we interpret the observations from Alpha Centauri. If we're looking for intelligence that thinks like us, communicates like us, has similar goals and motivations to us, we might miss intelligence that operates on completely different principles. Maybe those radio signals aren't attempts at communication, but are something else entirely, artifacts of information processing that we're misinterpreting as messages. Maybe the organized structures in orbit aren't built with purpose, but are emergent patterns that happen to be stable and self-sustaining. Or maybe, and this is even more mind-bending, the distinction between natural and artificial breaks down at certain levels of complexity. Maybe what we're seeing is a system that evolved naturally, but exhibits behaviors we'd call intelligent. Maybe intelligence itself is just a particular kind of natural phenomenon, not fundamentally different from weather patterns or geological processes, just operating at a different level of complexity. Dr. David Chalmers, famous for his work on consciousness and the hard problem of subjective experience, has suggested that consciousness might be more widespread in the universe than we think. In his panpsychism hypothesis, even simple systems might have rudimentary forms of experience, and complex systems like brains or planets or star systems might have correspondingly complex forms of consciousness. What if Alpha Centauri b isn't inhabited by conscious beings, but is itself conscious in some sense? What if the planet, with its complex chemistry and dynamic systems, has some form of integrated information processing that we might recognize as a kind of awareness? This sounds crazy, I know. But consider, the human brain is just a collection of neurons, none of which are individually conscious. Consciousness emerges from their interactions, from the patterns of information flow. What if something similar could happen at planetary scale, with chemical reactions playing the role of neurons? These questions aren't just academic. They affect how we approach the search for life and intelligence. They affect what we look for, what we expect to find, what we'd recognize as significant if we found it. And they affect how we think about ourselves. Because if consciousness and intelligence can emerge from diverse substrates under diverse conditions, then maybe we're not as unique as we thought. Maybe the universe is teeming with minds, with awareness, with experience, just not in forms we've been looking for. Or maybe we really are alone. Maybe consciousness is the rarest thing in the universe, an improbable accident that happened once on Earth and might never happen again. In that case, we carry an almost unimaginable responsibility. We are the universe's way of knowing itself. And if we fail, if we go extinct, we might be extinguishing the only light of consciousness in an otherwise dark cosmos. Both possibilities are profound. Both should fundamentally affect how we live, what we value, what we strive for as a species. So let's bring this home. Let's talk about what all of this means for you, personally, right now. Living your life on Earth in 2025. You woke up this morning in a universe that might contain other intelligences. You went about your day. Maybe you went to work or school or stayed home with family. You had breakfast. You scrolled through your phone. You worried about bills or relationships or health or any of the 1,000 mundane concerns that fill human life. And while you did all that, light was traveling from Alpha Centauri to Earth, carrying information about a world that might be unlike anything we've imagined. Radio signals were propagating through space, potentially encoding messages or meaning that we're only just beginning to detect. Does any of this change your daily life? Should it? Here's what I think. Yes. Not because it makes your concerns any less valid or important, but because it provides context. It reminds you that you're part of something larger than yourself, larger than your immediate circle, larger even than humanity. Dr. Carl Sagan, in his famous Pale Blue Dot speech, talked about how seeing Earth from space should humble us, should make us realize how petty our conflicts are in the cosmic scale. And he was right. But I think the potential discovery of intelligence elsewhere adds another dimension to that humility. If we're not alone, it means the universe is more wondrous than we knew. It means there are other perspectives, other ways of being, other experiences of existence. It means the story of life and consciousness isn't just our story. It's a universal story, one being written on worlds throughout the cosmos. And if we are alone, If these observations from Alpha Centauri turn out to have natural explanations, if we search 1,000 star systems and find nothing, then we are precious beyond measure. We are the universe waking up, looking at itself, asking questions. We are meaning in a universe that would otherwise be meaningless. Either way, alone or not alone, you matter. Your choices matter. How you treat other people matters. How you engage with the world matters. Because here's the thing, whether there's intelligence at Alpha Centauri or not, whether we ever make contact with alien civilizations or not, we have to build a future here on Earth. We have to solve our problems, climate change, inequality, conflict, disease. We have to become the kind of civilization that survives long term. And maybe, just maybe, if there really is intelligence at Alpha Centauri, they're watching us to see if we can do it. To see if we can mature as a species, overcome our self-destructive tendencies, become wise enough to be trusted with advanced technology and knowledge. Or maybe they're not watching at all. Maybe they're struggling with their own problems, fighting their own battles for survival, wondering if they're alone just like we are. The search for extraterrestrial intelligence has always been, in a deep sense, a search for ourselves. We're asking, are we normal? Are our problems typical? Is there hope for species like us? Can intelligence survive its own power? These observations from Alpha Centauri, whatever they ultimately prove to be, are part of that search. They're humanity growing up, looking beyond our own world, asking the big questions not just philosophically, but scientifically, with tools and methods that can actually give us answers. And you're alive to witness it. You're living in the era when humanity transitions from isolated to cosmically aware. Your grandchildren might live in a universe where the existence of alien life is confirmed fact, taught in schools, integrated into culture and philosophy and religion. Or they might live in a universe where we've searched extensively and found nothing, where we know with high confidence that we're alone, and where that knowledge has united humanity in recognition of our cosmic responsibility. Either outcome would be profound. Either outcome would change everything. So what happens next? How does this story continue? The James Webb Space Telescope will keep observing. More data will be collected. More analysis will be done. The spectroscopic signatures will be refined, the orbital mechanics better understood, the radio signals more thoroughly characterized. By the end of 2025, we should have a much clearer picture. The year-long coordinated observation campaign I mentioned will either confirm the anomalies beyond any reasonable doubt or reveal natural explanations that fit all the data. If the anomalies are confirmed, the next steps will be unprecedented. We'll likely see an international consortium formed bringing together NASA, ESA, the Chinese National Space Administration, and other space agencies to coordinate further observations and potentially plan more ambitious missions. There will be calls for a response to the radio signals, if they continue and if they're confirmed as artificial. That debate will be fierce, but it will need to be resolved. There will be philosophical and theological discussions as humanity grapples with the implications. Every religion, every philosophical tradition will need to integrate this new reality into their worldview. There will be economic implications. The space industry will be revolutionized if there's confirmed evidence of alien intelligence or even just complex life nearby. Investment will pour into interstellar research and technology. There will be cultural impacts. Art, literature, film, music will all be influenced by this discovery. New myths will be born. New stories will be told, and there will be personal impacts. People will think differently about their place in the universe. Some will find it liberating. We're not alone. Others will find it terrifying. What if they're hostile? Still others will see it as validation of beliefs they've held all along. But if the observations turn out to have natural explanations, if Alpha Centauri BB is just a weird world with unusual chemistry, if the radio signals are some astrophysical phenomenon we didn't know about, if the orbital structures are natural debris or some exotic form of ring system that will be important too. It will mean our models of planetary formation, atmospheric chemistry, and astrophysics need to be updated. It will mean the universe is more diverse and surprising than we thought, even without alien intelligence. And it will mean we keep searching, because Alpha Centauri isn't the only nearby star system. JWST and future telescopes will examine hundreds or thousands of exoplanets in the coming decades. We'll build up a statistical understanding of how common different types of worlds are, how often we see biosignatures, whether intelligence is rare or common. The search will continue regardless of what we find at Alpha Centauri. Because now that we have the tools to look, we can't not look. Humanity's curiosity won't allow it. Dr. Frank Drake, who formulated the famous Drake equation for estimating the number of communicative civilizations in the galaxy, said before his death, "The search for extraterrestrial intelligence is more than science. It's a mirror we hold up to ourselves. It forces us to ask who we are, where we came from, where we're going. And those questions are worth pursuing regardless of whether we find answers." I want to end by coming back to you. You've spent over 3 hours with me on this journey through the data, the hypotheses, the implications of what might be happening at Alpha Centauri. That's a significant investment of time and attention. What do you do with this information? How does it change how you live your life tomorrow? Here's my suggestion. Let it expand your sense of possibility. Let it remind you that reality is stranger and more wonderful than any of us fully comprehend. Let it motivate you to be curious, to ask questions, to not settle for easy answers. Let it inspire you to be part of something larger. Maybe that's the scientific community, contributing to our understanding of the universe. Maybe that's working on problems here on Earth, because whether we're alone or not, we need to build a civilization worth preserving. Maybe it's just being a better person, treating others with kindness and dignity, because we're all in this together, all inhabitants of this pale blue dot suspended in a sunbeam. The universe is vast. It's ancient. It's full of mysteries we're only beginning to unravel. And you're a part of it. You're made of star stuff, as Sagan said. The atoms in your body were forged in the hearts of stars that exploded billions of years ago. You're a way for the universe to know itself. That's not just poetry. That's literally true. And whether there are other ways for the universe to know itself at Alpha Centauri or anywhere else, your existence is no less remarkable, no less meaningful, no less precious. We've covered a lot of ground in this video. We've talked about the James Webb Space Telescope's capabilities, the spectroscopic anomalies detected at Alpha Centauri, the complex chemistry that defies our models, the organized structures in orbit, the radio signals that might or might not be artificial. We've explored hypotheses ranging from extreme life in hostile environments, to dead civilizations leaving automated ruins, to non-biological complexity emerging from chemistry itself, to the possibility of intelligence so alien we might not recognize it. We've discussed the philosophical implications, the personal meaning, the next steps in investigation. And through it all, we've been grappling with that fundamental question. Are we alone? Here's what I can tell you with certainty. We don't know yet. The data is intriguing, but not definitive. The observations are anomalous, but not conclusive. We're in that uncomfortable space between ignorance and knowledge, where the answer could go either way. But here's what else I can tell you. We're closer to answering that question than we've ever been. The tools exist. The observations are being made. The analysis is ongoing. Within your lifetime, we will very likely have an answer. And that answer, whatever it is, will change humanity forever. If we find that we're not alone, it will be the most important discovery in human history. It will fundamentally alter our understanding of our place in the cosmos, our sense of meaning and purpose, our conception of what's possible. If we find that we are alone, that life and intelligence are rare cosmic accidents that will be just as profound. It will place an almost sacred responsibility on our shoulders to preserve and protect the miracle of consciousness that has emerged on Earth. Both possibilities should fill you with awe. Both should motivate you to live a life of purpose and meaning. Both should remind you that you're part of something larger than yourself. The light from Alpha Centauri takes 4.37 years to reach us. The observations JWST made in 2024 are showing us that star system as it was in 2020. There is intelligence there, and if they're observing us, they're seeing Earth as it was in 2020 during the pandemic, during a time of global crisis and upheaval. What message would you want them to receive about who we are, what we value, what we're capable of? And more importantly, what message are you sending with your life right now, regardless of whether anyone else in the universe is watching? Because here's the ultimate truth. The search for extraterrestrial intelligence is really a search for meaning. We're asking whether the universe has purpose, whether consciousness and intelligence are common or rare, whether we're connected to something larger or fundamentally alone. And the answer to those questions isn't just out there among the stars. It's also in here, in how we choose to live, what we choose to value, how we treat each other and our world. The discoveries at Alpha Centauri, whatever they ultimately prove to be, are a mirror. They reflect back at us our own hopes, fears, assumptions, and aspirations. They force us to confront who we are and who we want to become. So watch the skies, follow the science, stay curious, ask questions. Don't settle for easy answers, but also look around you, at the other humans sharing this planet with you, at the life in all its diversity that has evolved alongside us, at the beauty and complexity and mystery of existence right here, right now. We're living in the most exciting time in human history. We have the tools to explore the cosmos in ways our ancestors couldn't imagine. We're on the verge of answering questions that have haunted humanity since we first looked up at the stars and wondered. But we're also living in a time of great challenges. Climate change, inequality, conflict, existential risks from our own technology. The questions we're asking about life in the universe are intimately connected to the questions we're asking about life on Earth. Can intelligence survive? Can consciousness persist and flourish? Can beings who have gained the power to destroy themselves choose instead to build, to create, to transcend their limitations? Whether there's anyone at Alpha Centauri or not, we need to answer those questions for ourselves. And the answer starts with you, with your choices, with how you live your one precious life on this one precious planet in this vast and mysterious universe. Thank you for joining me on this journey. Thank you for caring enough about these big questions to spend 3.5 hours exploring them with me. Keep looking up. Keep asking why. Keep searching for meaning in connection and truth. And remember, whether we're alone or not, whether the universe is teeming with intelligence, or we're the only ones asking these questions, your existence is a miracle. Your consciousness is a gift. Your life matters. Live it accordingly. If this video has changed how you think about your place in the universe, share it. Let's get more people thinking about these profound questions. And drop a comment telling me, knowing what you know now about the observations at Alpha Centauri, do you think we're alone? And more importantly, how does your answer change how you'll live tomorrow? The universe is vast and full of mysteries, but so are you. Never forget that. Until next time, keep wondering, keep questioning, and keep looking at the stars with hope and awe. We are, all of us, made of star stuff. And we're just beginning to understand what that really means.